Hello everyone. First and foremost, I'd like to thank Bodo's Power Systems for providing this opportunity to discuss Empower Semiconductor's ecap products, and thank you for joining me in this presentation. My name is Artin Minassians. I'm Senior Director of Engineering at Empower, and among my other responsibilities, I lead the design and development of integrated passive devices, including the ecap products. Ecap products are monolithic multi-capacitor passive devices with ultra-low equivalent series inductance or ESL that offer the highest density and most flexible solution for both power and signal integrity. They exhibit negligible derating for voltage bias, temperature, and aging, and from the height perspective, in the final assembled system, they can be as thin as 50 microns. ecap simplifies the design because it integrates multiple capacitors in a single device to save significant amount of space. And with millions of devices manufactured to date, it's a proven technology. One notable advantage of ecap is that, due to the negligible derating of the technology, all a system designer should do is to choose a nominal capacitance value that matches the required effective capacitance of the system. I'll explain this further with some diagrams. For a system that requires a certain amount of effective capacitance, if one chooses MLCCs, they should design for a much higher nominal value to account for tolerance and degradation due to voltage bias, temperature, and aging. This often requires multiple MLCC parts and the overall ESL is large, in hundreds of picohenry range. However, choice of ecap will require much smaller nominal capacitance because with negligible derating, one should account for the tolerance only. The nominal capacitance of an ecap is very close to its effective value with significantly lower parasitic inductance or ESL. This table summarizes the same discussion with a concrete example for about 44 nanofarads of effective capacitance. In case of an MLCC, the designer needs to set aside 30% for DC bias derating, 10% for temperature derating, and 5% for aging. Therefore, with the initial tolerance, 100 nanofarad nominal capacitance will be required. However, with almost no derating in case of an ecap, the required nominal capacitance, including the initial tolerance, is just 54 nanofarads. And this is about half of the nominal value of the MLCC. In the context of a buck converter, I'll explain the advantage of a low ESL capacitor for advanced systems of our modern days. The approach that I present here can be extended beyond a buck topology, and similar conclusions can be derived for any other power supply architecture or system. Here is a schematic diagram for our converter that includes the parasitic components of the low-pass LC filter. Often in low-frequency designs, the output capacitor ESL is ignored. If we analyze the transfer function of the LC filter here, we will see that at higher frequencies, its attenuation is capped at a gain that is a function of both L and ESL. For a given output voltage and inductor current ripple, this diagram with all logarithmic axes shows how the inductance and capacitance of the filter vary with frequency. Now, if we are designing for high-density form factors and are dealing with space-constrained systems, we need to increase the switching frequency to reduce the size of the filter components to acceptable levels. As a result, we are increasing the high-frequency gain of this filter, making it less effective at those high frequencies. In a buck converter, voltage waveform of the switching node Vx is a periodic pulse that can be approximated by its frequency component derived from the corresponding Fourier series. Therefore, we can replace the powertrain with a string of DC and AC sources, each representing one of the terms in the Fourier series. Since this is a linear system, we can then use the superposition principle and construct the output voltage by summing the responses of this LC filter to each one of its many input sources individually. Without loss of generality, for the rest of this presentation, let's ignore the DC component V0 and focus on the first 10 frequency components only. Let's consider a simple example. For a 10 millivolt output voltage ripple target, depending on the switching frequency, say from 100 kHz to 100 MHz, the LC filter can be realized with various combinations of inductance and capacitance values. Here I have selected 4 pairs to constrain the inductor current ripple within 1 amp. We can now plot the gain characteristics of the filter for each of these 4 cases. The ESR and ESL values chosen here are typical to the MLCCs that are used for such applications. Resistances R and ESR determine the damping of the LC filter that manifests itself as the peak value of the frequency characteristics at the resonant frequency. The higher the resistances, the higher the damping, and hence the lower the peak of the characteristics at the resonant frequency. For the 100 kHz switching frequency that corresponds to the large inductance and capacitance values, we can get a very good attenuation for all the 10 frequency components of the switching node voltage. As the switching frequency increases, attenuation of the higher harmonics is further degraded. But at really high switching frequency of 100 MHz, where we can truly miniaturize the system for full integration, we notice that all the frequency components are attenuated at the same limited level. That means a scaled-down version of the switching node voltage, a pulse that is 36 times smaller than Vx, will show up at the output of this regulator. For a 3.3 volt input voltage, or Vin, this corresponds to more than 90 millivolts of ripple, which is unacceptable for a design target of 10 millivolts. It's worth noting that increasing Cout capacitance will not reduce this ripple because it's a limitation caused by the parasitic inductance ESL. To enhance the attenuation with MLCCs, often additional parallel capacitors are added to reduce the equivalent ESL. In practice, due to the board parasitics between the adjacent capacitors, this approach shows no or minimal improvements. This graph demonstrates that if the MLCC is replaced with ecap, the ultra-low inductance of this technology will significantly improve the filter performance and will enable the high-frequency operation of the converter. A high number of parallel MLCC capacitors would be required to match the performance of the ecap solution. The intrinsic ESL and ESR of an ecap are very small, but the actual values of these parameters for an ecap device are closely linked with the way the ecap is integrated into the system, that is, the design and assembly constraint of the application substrate. In this graph, the ESR and ESL values correspond to an ecap device that is designed with 2 pads to match an 0402 package footprint. Finer pad size, shorter pad pitch, shorter pad height, and higher number of pads per capacitor will result in lower ESL and ESR. In conclusion, as the demand for high-performing capacitors grow rapidly in various markets, applications, and functions, ecap proves to be superior in density, size, electrical characteristics, stability, flexibility, and reliability. The focus of this discussion was on the crucial role of low parasitic inductance in providing a high-quality, steady-state voltage at the output of a switching regulator. In future opportunities, I'll discuss the impact of improved parasitics on the dynamic behavior of a converter. Finally, I'd like to acknowledge the contributions of my team members who are doing an impeccable job in making impossible possible. Thank you for being a part of this discussion. Please feel free to reach out to me at the email address shown on the screen should you have any comments or questions.